My professor, Nick Cassimatis, couldn't make it today, so I'm going to present for him. So save the hard questions to him, I guess. I'm a third-year grad student, and Magda works in Naval Research Lab right now, and she's also part of the Human Level Intelligence Lab. So this is one place I can say that without being threatened by people, I guess. All right, to motivate. Our work is about, like, Nick Cassimatis has a cognitive architecture called Polyscheme, which he focuses on cognition in general, and I work on how to map language onto that architecture, or how to use that architecture to give us natural language understanding. So this is just a motivation of saying why natural language understanding is hard. So the computer is called Coyote, and there was a yellow blob that just moved. That's Elmer, and so somebody tells him that the orange blob that moved, this is Elmer, and now they're asking the Coyote where Elmer is, and so he's looking around, looking for the orange blob, which Elmer would be, and Elmer comes out of the occluder, which is the green part, to the left. So Elmer was on the right in the beginning, and then he moves to the left. He should be out anytime. All right, there he is. And so now somebody asks Coyote where Elmer is, and so he's looking, and he finally figured out that Elmer is over there. And so, right? And eventually, this Coyote goes and checks that Elmer has a path. So he says, this might be Elmer, the orange block. And he's going towards Elmer. So this is funded from Naval Research Lab, and that's the citation where it is. Okay. He goes closer, and he finds that there's actually no path for Elmer to get from the right to the left. And so that gives him incentive to say that this cannot be Elmer, and Elmer has to be somewhere else. Right? So what was hard in this whole process? Right? First, someone is giving instructions about this is Elmer, right? And this is a social cue that says whatever we're focusing on at the same time, the common goal or the pointing is Elmer. And then there's language involved, and there's visual information. So the moving blob should be thought of to be Elmer, right? And there's concepts like space, path, planning, and occluders, and objects, not interference of paths. So a simple problem is not so simple after all. And if this is what we want a language understanding system to do, it has to include all these components to it. Social, inferring goals, social cues, integrating vision information. So why is this hard? Right? This is how we've come to think of, not us, but in general, people have come to think about mind. That there's a module for language, a module for vision, a module for motor, and they all are separate and very tightly integrated within themselves. But I talk to a central mind processing system that just puts them together and gives us an answer. This is not feasible in the sense that we see lots of cases where everything is so tightly integrated. So what is it if language was supposed to talk to the mind central processing system? What would its input-output be? Because it needs much more than that, right? So how does language possibly interact with the rest of cognition? That's the theme. This type of system engineering modules has led AI to have different standards too. So the dialogue system and the NLP we've been hearing about is not the standards anymore. If I go to a AAAI conference, the most of the things I hear about is PCFG, how much accuracy did you get, part-of-speech tagging. Narrow problems in the sense that they do work on a lot of data, but they're only very specific, and they have metrics like precision and recall. So people claim that there is 90% precision in recall in parsing, but when you look in the statistics, the exact matches, or the number of times they actually get the entire sentence correct, is 20 to 40%, and nobody ever talks about that. So our standards have kind of shifted. It's because of our architecture like this, we can't can't do complicated integrated problems, and we have gone into the path of justifying results and numbers that don't mean too much anymore. So why is this hard? How are we dealing with it? So we believe that integration and close working of different domains or social what are they? Different inputs should be done. And our approach to it is the cognitive architectures or the cognitive substrate. So there's two beliefs. One, that there are a basic set of processes or a mesh of representation and processes that underlie cognition, and we call that the substrate. And two, that most of the problems like language, social cognition, physical reasoning, planning can be mapped on or represented in terms of the substrate. So there's the aim of the lab is twofold. First, to improve the substrate, and second, to map different problems onto the substrate. So language mapping is a substrate mapping problem. This is what we think the substrate could be, our first guess at it. So there's a small focus of attention with very tightly integrated modules that can interrupt it at any time. And let's say, so our modules are not language or vision. They're more basic concepts like how do you handle time or category or identity or processes like that. And there's Nick's citation for it. Right? So that's one of the substrate defining problem, and this is more the mapping problem. So even if we do not get the details of the substrate correct, once we have the substrate, how can you solve language? How can you map social cognition? So that's a more theoretical endeavor. And there have been different mappings. The first one is physical reasoning. So it's more about how objects interact and how young kids track objects, more spelky objects, Bayesian kind of stuff. And that was done with Professor Nick's PhD thesis. And we do word learning. Magda's working on that. And social cognition is also mapped onto polyscheme. The same stuff I'm going to show you how I've mapped language on is also used for different things like this. So it gives us more plausibility in that this substrate can be used in different domains. Alright, so this is an example, since I'm not going to go into any detail. So this is just an example of how a sentence structure can be thought of in domain general terms. Right? So there's the dog John bought bit him, right? Okay. And so all the sentences, so every word can be thought of as just another event, like a button click event, or not specific to language, just any other event. And the nodes in the tree can be thought of as higher or composite events that have parthood relationships or metonymy to them. And so this is how we represent it. And identity, so the same thing, the dog John bought bit him, so the dog bit him. Him here refers to John himself. So the referent object of both cases are the same person, so identity ties into, and there's time information too. The words have to be sequenced for us to parse the tree. And so a lot of language-specific details can be thought of in more general terms. So for example, the word can be thought of as just another event, and constituency of phrases can be thought of as parthood or metonymy, and we have more complex objects than just in language. And what else? Phrase attachment is just identity of events, and co-reference binding is actually identity of the referring object that we ground things to. And traces is just, so traces like pronoun reference or traces or just object permanence, and dependencies are just relations, long path relations.
So you know that's it too.
Okay, good. All right. So what have we done? What is the benefit of all this? Just 2 minutes. One of the easy benefits that we can easily show off is that the same framework is used to both model syntactic constraints and semantic constraints, and everything is within the same framework, vision, and all of them are represented within the same format. So one of them is syntax and semantics integration. So let's say this is an example where the bug needs a battery, and a bug can have
one of 5 meanings, say, and everything else is not ambiguous, let's just assume that. So one of the more common meaning being the insect, animal, and the lesser common being the system error, a listening device like the spy bug, and annoyed and word sensitive, right? Okay. So using default logic, since we have an ordered list, we can say that by default it's always the animal, but if it's not the animal, if the animal sense is blocked, then it's the system bug and so on. Okay. So when semantics kicks in, we know that battery is an inorganic substance, and that only inorganic substances only inorganic substances might need battery, and people don't need battery, or organic things don't need them. So information is stored in a category hierarchy. Then we have 2 competing sources. One that says that because of the sentence's meaning, the bug should need a battery, and because of the underlying semantics that usually things that need a battery or tend to be inorganic. So both of them conflict, and the meaning and the default meaning of animal bug, it leads us to a contradiction which we have to resolve. So this is no extra work, just the advantage of having both syntax and semantics within the same framework. And we can do lots of other examples like people's beliefs playing it within language, and vision and pointing to stuff and social references are all part of language, and we can show how accuracy, or we can actually parse sentences, handle sentences like that. All right. Thank you. So by just this mapping, we hope to show that we can create systems that are general and can integrate different domains. And for details, you have to read our papers on the architecture and so on.
Thank you. Let's give her a